Okay, so our next topic is growth and decay models within the exponential function unit. So what are some situations that can be modeled with exponential growth and decay? And actually the pandemic that we're in with the COVID-19, it is an exponential one. The whole stay at home, stop the spread is basically to stop this graph from growing exponentially. So you are living in a real world exponential function right now. We're trying to make it not be as steep of a function by staying at home and not spreading it. Okay, but this is what the general equation looks like for an exponential growth or decay. The A value here is your initial amount. So whatever your initial number is. So it's either the initial population or the initial money you start with, or whatever the starting amount is, that's the number that goes here. And then you do 1 plus. So if it's a plus sign, it's a growth. If it's a minus sign, that's because it's decay. So depending on what the situation is, you'll either use positive or negative. R here is your rate, which is usually given as a percent, but you need to change it to a decimal. So that's what we're going to be doing with these percentages. And then T is your time, usually in years, but it doesn't have to be. It's whatever the units say, but usually these are in years. Okay, and then occasionally you'll get the whole thing here. This is what we just got done seeing on the tables in the last section. The whole base is called your growth or decay factor. So this is your multiplier, what's being multiplied in your table to go from one to the next one. That's the entire base. If it's growth, it's more than 1. If it's decay, it's less than 1. So that's where the plus and minus comes in. Okay, so what I'm going to do is I'm going to do one example of each. There's 4 different models total. So I'll do one of each, showing you how to set it up and put it in the calculator. And then at the end, or on the next section, I'll come and just throw a bunch of examples, and you got to decide which one it is. Okay, so looking at this example 1, I'll come to the table in a second. It says, in the last 12 years, an initial population of 38 buffalo in a state park grew about 7%. So the first thing we need to do is decide if it's growth or decay. So this one, it obviously says it grew. This one has to be a growth, which means we're going to use the A times 1 plus R to the T. We're going to use the positive one. Okay, so the A value is your starting amount. So we started with 38 buffalo. And R is your percent, but you want to change this to a decimal. So if it's 7%, if you divide that by 100, you get 0.07 as your decimal. Okay, so what's our model? That's just plugging in the A and the R in this equation. So N equals A is 38 times 1 plus R is 0.07. And then T is time for the X variable. Okay, so if we add these together, our model is 38 times 1.07 to the T. So we're going to use this to answer part B and to answer the graph one at the bottom. So this is where you're going to need your calculator. At part B here, we want to use that model to estimate about how many buffalo were in the state park after 7 years. So 7 here is going to be our T. So our equation was 38 times 1.07 to the t is going to be 7. Okay, so in our calculator we just type this in. So 38 times 1.07, exponent is the little caret sign, and then we do 7. And we get this decimal right here. So 61.0197. But again, we're talking about buffalo. So when it's the number of something, you round to the nearest whole number. So here, I would just say there were approximately 61 buffalo. If it's money, you round to 2 decimals. If it's number of, you round to the first decimal. Okay, and then for this one, we need to graph it. Let's see how this one's different in the equation. We're going to need the graphing calculator to graph it. Okay, so it says estimate the year. So I'm looking for t. So this is my t. I want to know what is t when there were 53 buffalo. So the 53 here is giving me the n. So the n is 53. And I want to see when is that equal to my equation, 38 times 1.07 to the x power. This is what I'm looking for. I'm looking for x. We don't know how to solve this by hand yet. Okay, we don't divide by 1.07. It's not going to work. The only way we can solve it right now until we get logarithms is by graphing it. So over here in your calculator, we want to graph this equation. So get a new graph. So new, no, I don't need to save that, I want to graph. So in the first one, you're going to put your equation, the 38 times 1.07 to the x power. And then in another equation, so tab to get another one, we want to know when is that 53. So notice if you leave it here, you're not going to see it because these are all the way, I mean, look what these go by. These go by 20s. So we're going to need to drag this in order to see it. I don't want to drag the text, I want to drag the window. So notice here, if I drag it a little bit, I'm able to see the two graphs. So just pull the graphs, whichever direction you're trying to go. I just need the top part. What I'm trying to find is where they intersect. So here, let's see, you just go to the graph, and you should be able to see the intersection. Come on, get in there. Okay. Okay, so to calculate the intersection, you go to the menu, you go to Analyze the Graph, and you choose the intersection. And it's going to give you a dotted line. It's asking for like the space that you want to find the intersection. So you put one on the left side of the intersection, and then on the right side. And then it says, in this area, do you want me to find the intersection? And yes, it's that point right there. Okay, so I really only need the x value. So the x value is 4.92, which this is in years. And for our purposes, we can just say it's about 5 years. But this one would give you the exact one. Okay, so I'm just going to sketch the graph here. So this horizontal line is at the 53. So at 53-ish, draw like a horizontal line. I mean, if you want, you can go get the table and get more exact answers, but you don't need that for this one. So for the exponential part, it's a little hard to see what this goes by. I know it started at 38, so that's my y-intercept is at 38. And then it's just going to go up from there. So at 38, it just goes up. And we see that it intersects about 5 years. So 4.92 exactly, but if we round it, it would round to 5. Okay, I don't need you to be able to graph this exactly. I'm just graphing it here to show you what to look for in the calculator. So in the calculator, you graph one side in y1, or f of x1, and then this side in f of x2. And then it was min u, and then you go to number, to analyze the graph was which number? Min u, and then analyze the graph is number 6, and then you choose number 4, intersection. So min u, then you choose number 6, which is the analyze, and then you choose number 4, which is the intersect. And then you do the left bound, right bound. So you put it a little bit to the left, press enter, put a little bit to the right, press enter, and then it'll calculate the exact one. Okay, so that was a growth. Now let's come over here. Let's skip these examples. We'll come back to them just by doing some extra practice. But let's look at number 3. So number 3, it says, in a new television costs $1,200. The value decreases by 21% each year. So if it decreases, that means it's a decay. So we're going to be using the a times 1 minus r to the t. We're doing the subtraction one because it's a decay problem. Okay, so the a is your starting number. So what was the starting cost? It was $1,200. And then the r, 21% divided by 100 is just 0.21. So we're going to do y equals, or n equals, a is the 1,200 times 1 minus r is the 0.21. And since it's a model, we're just going to leave it with t. We'll plug in t for part B, but for this one, we'll just leave it as t. Okay, so if I actually subtract this, we get 1,200 times 1 minus 0.21 is 0.79 to the t. Okay, so if I ask you what the rate is, this is the rate right here, this is r. If I ask you what the base is, or what the decay factor is, that's this part right here. So this part is the decay factor. So it depends what the question asks you. If it asks you for the rate, that's r. If it asks you for the decay factor, that's the whole base, which is the 1 minus r part. Okay, so now we want to use this model to estimate it after 2 years. So for the 2 years, we're going to plug in 2 for t. So we get 1,200 times 0.79 to the second power. And you go to your calculator and we just get this value. So let me get back to my, I don't need to be here. So back to my calculator. So 1,200 times 0.79 to the second power. And this one, since it is money, so we're talking about the value, we're going to round to 2 decimals. So here, 4,748 and 92 cents. Of course, if you were selling it, you'd probably not post that exact amount. You'd say 750. But, you know, for the calculator purposes here, if we can get the exact answer, we can always round it later on. So for money, you round to 2 decimals. For number of, you round to the nearest whole number. Okay, so that's how we do that one. And then again, part C is using the graph to find the value. So what was our equation again? 1,200 times 0.79. And we're looking for the time. We're looking for when this is equal to 300. So for the 300 part, we know that's going to be a flat line at 300. And then we need to graph this one to see where it intersects. Okay, so again, going back to your graph. I'm just going to clear everything. So new graph. So I'm going to put this equation 1200 times 0.79 to the x power as my first equation. And then tab for my second one, I want to know when is it 300. Enter. And again, you're not going to see it in this window because these go all the way up to thousands. So you're just going to need to adjust it. So pull value until you see the graph. I don't want to pull both of them. I just want to pull the y's. Okay, so I see that one now. Okay, so you can keep pulling until you see the intersection. Since we have an exact window here, we can actually make this the exact window. If you go to menu and you go to window and you put the settings, you can actually change it to be this. So the min x value is 0, so 0. And then here the max x value is 9. One more would be 10. So here just 10. And then on the y's, this is, I mean, you really don't need to change the scale, but these go by ones. These go by 200s, but you really don't need to change that part. The y minimum is 0 again. And the y max, if I'm counting by 200s, would be 1400. And we get a better graph that looks like this one. Okay, so we see that this one starts up here and it goes down because it's decay. It actually starts at 1200 and it goes down, something like that. We're trying to find this value. I don't know if it's 5. But this is what we did before. So you go to menu, you go to analyze, number 4. You put this one anywhere to the left. It doesn't have to be like right to the left. And then to the right. And let's see if I can make this thing go away. There's a lot of clutter there. Okay, so there's this equation, the 300, and this is my intersection. So that's telling me that the time that it takes, so x is 5.88. Which again, if we round it, we would just say 6 years. So my graph is a little off, but that's what we're looking for in the calculator, is where they intersect. Okay, and then from here, you can do two things. You can go back and plug it in for 15. You can plug 15 in for x, or since we have the calculator right here, we can just look at the table. So if we go Control T for the table, we can just go to 15, and go to 15, and then we have our y value. So, I can't see that. What is that number? So I get 38. So here we did 1200 times 0.79 to the 15th. We're looking at the 15th. Since this is money, I round to 2 decimals. So this is $34 and trying to see what that is, 96 cents. Oops. Okay, so then it asks, is this reasonable? Probably not, more than likely not. You know, after so many years, it's not worth very much. I mean, it's probably not worth anything except parts. Or maybe it turned into a classic and it's worth way more than that. So you got to be careful. You can't just keep this graph going on forever. The graph itself goes on forever, but the interpretation of it doesn't necessarily go on forever. At some point, it's gonna mean something else. So be careful. That's called extrapolation. When you go outside the bounds, you're extrapolating data that's not in a reasonable range. Okay, so that's growth and decay. There's two other models, the compounded interest models. So that's part 2. But that right there will give you enough to do growth and decay. So these other ones that I'm going to do a couple more problems. They're just more examples of that. Okay, so over here, going back to number 2. So in 1996, there were 2,573 computer viruses and other security incidences. During the next 7 years, the number of incidences increased by 92% each year. So again, first, we got to decide, is it growth or decay? Increased means it's growth. So we're going to do the 1 plus r to the t. A is your starting number, so here we started with 2,573. And R is your rate, 92%, but as a decimal would be 0.92. So plugging everything in, we get N equals A is 2573 times 1 plus, since it's growth, R was 92, so 0.92. And we're going to leave this as T. So we just add 1 plus 0.92 for our model. So 2573 times 1.92 to the T power. So from here, we just use it to calculate these values. So for this one, we're just going to type it in the calculator. So notice this started in 1996. So we're not going to plug in 2003 into the exponent. We want to know how many years have passed from 1996 to 2003. So 2003 minus 1996 tells us, if we subtract these, that T is 7. So when we subtract, we get 7. Never plug in a year into the exponent. You will overload the calculators, and it's going to give you an error because the number's way too big. So you have to subtract them to see what the T value is. So that's what we're going to plug in here. So 2573 times 1.92 to the 7th power. So again, go grab your calculators. And just start it all over again. So 2573 times 1.92 to the x, or not x, to the 7. And we are getting, so we don't want to round, or we don't want a decimal, because we're talking about the number of incidences, the number of viruses it had. So you don't have half a virus. You have a virus or you don't. So here we just want the nearest whole number, which is 247,485 computer viruses and incidences. Okay, so number of, you round to the nearest whole number. Money, you round to 2 decimals. Alright, so then this one has a graph as well. So you're not always going to have a graph question and a plug-in question. I just want you to know how to get the answers in the graph. Okay, so this one, it's a little tricky, you really can't tell by the picture here, but the x's go by 1s. So if you want to use that Windows option, these go by 1. So 1, 2, 3, 4, 5, 8, 9, 10. I mean, you can kind of use this to estimate it right there, but these right here go by 50,000. So 50,000, this one would be 100,000. This is 150,000, and then 200,000. So you can use that for your window. So what are we plugging into the calculator? On one side, we're going to plug in the equation. 2,573 times 1.92 to the x power. Make sure you do plug in x. If you plug in the number, it's not going to graph the exponential shape, it's going to graph a horizontal line. And we want to know, when is this equal to the 125,000. So here, plugging it in. So we want the graph. Y1 is the 2573 times 1.92 to the x power. And we want to know, enter, when is that equal to the 125,000. So tab 125, 1, 2, 3. Oops, that's too many. 1, 2, 3. So in the regular graph, you're not going to see the intersection. So you have to change the window either by dragging and zooming out or by coming over here and adjusting the settings. So this goes from 0 to 10 again. Usually that's what it's going to be. Otherwise, you're going to be extrapolating data. By ones, okay, auto, that's fine. And then here, this one goes 0 to 200,000. And you see this graph. So again, in order for us to find that intersection point, we have to go Menu, Analyze, Intersection. So go to the left a little bit, go to the right a little bit, and it says that this is our intersection. So again, you just go a little bit to the left, a little bit to the right, and it's saying that this point is 5.95, and then we really don't care what this decimal is. This is the answer. So if we round that one, we can say that it's about 6 years. I mean, we can see that from the graph. It's right there at 6. But to find the exact one, you do the intersection. Okay, and then we have one more decay model. Okay, so example number 4 here. Probably get all in one. It says a new snowmobile cost $4,200. The value of the snowmobile decreases by 10% each year. So again, growth or decay. Decreases is decay. Another word you'll see is depreciate. If something depreciates, that means, it's going down. It's getting lower. So decay, depreciate, decline, all those mean decay. So we're going to do 1 minus r to the t. Okay, so what is the A value? The starting amount is 4,200. So 4,200 is the first one. Times 1 minus, we need r. So r is 10%. 10% as a decimal would be 0.10, 10. So we're going to subtract 0.10 and leave it to the t power. So 1 minus 0.10 is 0.9 to the t. Alright, so estimate, use calculator to estimate the value after 3 years. So 4,200 times 0.9 to the third power. So we just go type this in. So 4,200 times 0.9 to the third power. And again, we're dealing with money because this is the value. So money would be $3,600 $61.80. 8 rounds, 8, we would just put 80 for the cents. Okay, so in a graph over here, we have a decay graph. So again, it's going to be 0 to 10 this way. And then this value is the starting amount, which is the 4,200. So the very top of it is going to be 5,000, I think. Let me double check that. So it goes, we're going to have a flat line at 2,000, so 1, 2,000. And then this one is the exponential decay, and we're looking for that point right there. So let's just go get our graph one more time. So 4,200 times 0.9 to the x power. And then tab to get your other one. We want to know when it's 2,000. Oh, what happened to it? Tab 2,000. Too many zeros. Okay, again, this one, you might be able to drag it and see, but if dragging it doesn't work to see the numbers, then to see the intersection, then you need to go change the window. Sometimes dragging, you can't get a nice window, so I can't get it here because I can't hold it. So I'm just going to go change it. 0 to 10. Again, that's usually the x's. You can't go too far into the future here. 0, because it can't be negative value. And then it goes to the 500, or 5,000. And let me get these out of the way. So we're looking for the intersection here. Again, if I don't give you the graph, you just have to make sure that this number is bigger than the number you're looking for. If the max is bigger than the number you're looking for, you'll be able to see the intersection. So menu, and then we're looking for the intersection to the left, to the right, and it tells us that it's 7.04 y. And I don't care about the y, I care about the x. Alright, so again, the answer to 2,000 equal to 4,200 times 0.9 to the x is, we can just say about 7 years. Okay, so that's growth and decay. Like I said, there's 2 other models we need to talk about. But look for those keywords: decreases, increases, declines, depreciates, things like that, to see which one it is, and then you just set it up. Okay, but you are going to need a calculator to type these in.